In this problem, we have a very special bond of 200,000. This is the nominal amount, and it's bearing interest of 10% per annum payable half yearly. So interest is the cost that you incur because you borrow money from people. So it's useful to make a distinction between this concept and the yield. So the yield is a measurement of how well an investment is doing. So it's useful to make this distinction. So this is essentially the coupon rate. And this loan will be redeemed at par by annual installments starting at the end of the 5th year. And this is what makes this bond special. So normally if we have a bond, let's say we start off with a nominal amount of 200,000. After n years, what we will essentially have in the meantime, in the middle, we have these annual payments of coupons. So these payments of coupon, these are the cost that you incur because you're borrowing money from people. And at the end of the nth year, so this is an n-year bond, after we pay off this final cost of borrowing money, we also pay off a redemption value to settle this debt. So we pay off this redemption value, and then we settle this debt, and then this account is closed. But in the problem that we have here, so this is a very bad line. So the problem that we have here, we're told that the debt is settled by annual installments of 10,000. So what that means is that we start off with 200,000 nominal value. In the meantime, we still keep on paying these coupons, which is the cost of borrowing money. And at the start of the 5th year, you start paying off, apart from the coupon so coupon is the cost of borrowing money, you also pay off a bit of the nominal amount. So you pay it off in the form of a redemption value of 10,000. And since it's redeemable at par, each time we pay off this $10,000 par value, we're also lowering the nominal amount by 10,000, so it becomes 190,000 after this payment. And this keeps on going, and as you know, when the nominal amount goes down, the amount of coupon that we pay also goes down. So the nominal amount goes down, the amount of cost that we incur for borrowing money also decreases. So the coupon that we keep on paying in the future, it keeps on decreasing because the nominal rate keeps decreasing. And if we use the regular methods that we've been using to calculate the price of the bond, this would be very complicated. So here we're being asked to find the price of the bond, and if we use the normal formulas, this would get really complicated because the coupons keep decreasing. So the trick here is to use Maykamp's formula. So this is the bond that we just encountered right now is what we call a serial bond. And a serial bond is exactly the type of bond that we have right here in this question. It pays off the nominal amount by annual installments. So the nominal amount keeps decreasing, and this is a serial bond. And whenever you encounter a serial bond, always use Maykamp's formula. And in this problem, you'll see why. So this is Maykamp's formula, but in our case, we also have a 40% tax rate, so we need to incorporate that as well. So the reason why we use Maykamp's formula is that this formula does not have to deal with time. You don't have to deal with the amount of coupon that we pay. So for the usual formulas that we use, we always have a symbol like this, and then in the front we have the amount of coupon that we pay. But since the amount of coupon that we pay in this situation keeps on decreasing because we're paying off the nominal amount bit by bit every year, using this symbol would be really complicated. So that's why we can use this formula to better kind of encapsulate the entire bond. And just now I said we don't have to deal with time in this formula, so we don't have to deal with time in the form of this index over here. So when we deal with this, we need to specify how long the coupons last, and since the coupons keep varying, this isn't very practical. But now all the information about time is encapsulated within this amount k, so using this is much better than using the normal formulas. So to calculate k, which is the present value of all the redemption values, as you can see, the redemption values start off at the end of the 5th year. So let's just draw a timeline for that. Starts off at the end of the 5th year, and then it keeps on going, and you can imagine if you're starting at time 4, because at this point you have a nominal amount of 200,000, there would be 20 of these redemption values of 10,000 in the future. So you can guess that this ends at time 24. So the present value of all these redemption values is just as we would normally calculate the present value of our annuity immediate, because since we're paying off, since we're paying the redemption by 10,000 per year, this is essentially, if you're standing a time for, an annuity immediate of 20 years. So if you discount all this back to time, using this formula, you discount everything back to time 4, and you bring it back to time 0. So you also do v to the power of 4. So this is your k. Now your c is the total amount of redemption value that you pay, and since this is redeemable at par, by the end of this entire thing, you would have repaid this entire nominal amount, so the c is just 200,000. So if you substitute all these numbers into your formula, so don't forget you also need to find your g and your I, and in this problem, we're given, so in this problem, the payments are done half yearly, so as usual, we'll just take the half of this. So the coupon rate is 5%, it's redeemable at par, so the g is also 5%. And the yield is 8%, once again, this is half yearly, so we get 4%. So substituting everything into this formula, we can find our price P. And also don't forget, because this 4% over here is the rate, is the amount of yield half yearly. The interest that we use for this formula is going to be 1.04 square minus 1. So because the redemption values are paid yearly, but only the coupons are paid half yearly, so that's why we need to use this interest rate for this symbol over here. So make sure to not fall for that. So once you've substituted everything inside the formula, you'll get the answer. So 167,000.